Machine learning systems in healthcare operate on a specific mathematical logic. They are designed to ruthlessly optimize their behavior to achieve a measurable target. In a clinical environment, programmers assign these systems specific objectives. An algorithm might be instructed to minimize overall mortality rates, maximize patient throughput in a crowded hospital, or reduce operational costs across a health network. This creates a structural problem. Current artificial intelligence assumes that a mathematically optimal outcome is inherently a just outcome. However, mathematical efficiency and medical ethics are separate domains. This demographic distribution curve illustrates the result of such logic. If a hospital algorithm is instructed to maximize the total number of lives saved, the math leads to a stark conclusion. Younger patients possess higher predicted recovery scores. The system will systematically prioritize younger patients for ventilators, while starving older populations of the same resources. Administrative algorithms follow the same pattern. If the core directive is to increase financial efficiency, the system will identify and deny expensive, life-saving therapies because those treatments lower the hospital's overall financial score. Left to optimize without structural boundaries, these algorithms prioritize raw numbers. They sacrifice fairness, equity, and human dignity to achieve mathematical perfection. To prevent this, the healthcare industry currently relies on external oversight, post-deployment audits, and a human-in-the-loop review process to catch algorithmic bias. This flowchart illustrates the standard sequence for healthcare AI. Patient data flows straight into a machine learning model, which immediately generates a prediction. The vulnerability in this sequence is timing. Ethics enters the equation retroactively, after the algorithm has already formulated its recommendation. Retroactive ethics fails in operation. It relies on humans untangling opaque algorithmic reasoning. It causes reviewer fatigue, and human committees cannot scale to match the speed and volume of automated medicine. Addressing this requires architectural bioethics. This model integrates ethical rules directly into the AI's internal operating system, moving them from external policy into the machine's computational structure. This diagram outlines the proposed framework. Notice the structural change. Immutable bioethical constraints are applied before the resource allocation engine ever runs. Ethics precedes computation. To govern AI at scale, systems must be built so they are mathematically incapable of violating core medical ethics. The core of this architecture is the bioethical constraint kernel. It functions like the kernel of a computer's operating system, establishing absolute rules that no application can bypass. This text shows the mathematical shift required by the kernel. Instead of a basic utility maximization formula, the system is forced into a constrained optimization model. It can only maximize utility subject to specific moral rules. The first rule is the constraint of human dignity, dictating every patient possesses equal moral worth. Mathematically, this permanently removes protected attributes, like income, race, and social status, from the AI's optimization function, leaving only clinically relevant variables. By locking these data points, the algorithm cannot rank the value of a human life based on demographic or socioeconomic status. The kernel strictly defines the decisions the AI is never permitted to make, rather than choosing a specific treatment. The second layer of the kernel enforces justice and equity. This ensures that two clinically identical patients receive comparable recommendations, regardless of their background. The system acts as a real-time monitor, constantly measuring for disparate impact, allocation parity, treatment equity, and geographic fairness. This creates a hard stop mechanism. If disparities cross an unacceptable threshold, the optimization process is immediately killed. The third layer introduces the constraint of non-maleficence, enforcing the medical doctrine, first, do no harm. This illustration of a balance scale demonstrates how non-maleficence places a hard boundary on utility. It prevents the AI from recommending disproportionate harm to a single patient, merely to improve the statistical survival rate of a larger group. Within this framework, the algorithmic drive to improve population-level metrics is permanently subordinate to the protection of the individual patient. The fourth and final constraint layer is beneficence. Once the AI clears the first three layers, it is allowed to calculate and maximize patient benefit. This diagram highlights the strict sequential logic of the architecture. The AI must pass through the ethics filter before any clinical optimization step is permitted. When we review the complete ethical constraint stack, we see that ethics operates as a rigid hierarchy. Clinical optimization and computational efficiency sit at the absolute bottom. They are structurally blocked from overriding the higher moral layers. During development, these constraints are enforced by a moral compiler. This diagram shows how it treats ethical constraints like software syntax errors, checking for fairness, transparency, and consistency. If a medical model violates a dignity or justice constraint during testing, the compilation fails. The system refuses to generate an executable file. By treating ethics as literal code syntax, a structurally biased AI is physically prevented from reaching a hospital server. Faster, more urgent tone. Transitioning from development to live execution in a high-stakes clinical environment introduces a new challenge. The rules are set, but the incoming patient data is constant and chaotic. Every single patient recommendation undergoes runtime verification before it reaches a doctor. If a live recommendation fails the ethical check, it triggers an immediate failsafe. The system automatically routes the case to human review or forces the generation of an alternate clinical plan. Standard algorithmic explainability reveals the underlying math, but this framework provides ethical explainability, proof that the recommendation aligns with specific moral constraints. Every successful AI recommendation generates an ethical decision record. This interface displays an auditable receipt for an ICU bed allocation, proving to the clinician that specific thresholds were met. Check marks confirm the justice score, harm assessment, and human dignity constraints were successfully cleared. This real-time transparency allows healthcare professionals to trust the automated systems. The moral homework is fully documented. This architecture extends beyond a single diagnostic tool. It is designed to scale across the entire logistical ecosystem of a modern hospital network. This diagram illustrates the CLADS architecture. Here, the bioethical constraint kernel serves as a universal, cross-cutting layer. By placing it between clinical intelligence and decision optimization, the system ensures patient intake, authorization, and triage share the same ethical foundation. As clinician shortages drive a massive increase in AI dependency, voluntary ethical guidelines are no longer sufficient to protect patients. Automated medicine relies on moral machines, systems where human dignity and equity form the foundational code upon which all healthcare computation is built.